Derivatives of inverse circular functions. So if you want proofs of these patterns, you can look in your textbook. These are also on the formula sheet at the end of the year, so you don't have to remember these. So if your function is fx is sine -1 of x, then the derivative f dash x looks like this. It looks like 1 over the square root of 1 minus x squared, and of course there's a restriction on x. X needs to be between -1 and 1, which of course is the highest and lowest values that sine can take. Now if you add a dilation into that, so fx equals sine -1 of x on a, then it's similar. The derivative still 1 over, but where the a ends up is in the bracket, under the square root, where that one was. And this time the restriction on x this time is that it's between -a and a. Alright, so it's the sine one. The cos one is very similar. So cos -1. Alright, so if fx is cos -1 of x, then the derivative looks very, very similar, and the difference is that -1 up the top there. Again, of course, x has got to be between -1 and 1. And then if you stick a dilation in there on your x, then again we'll do it as x on a, and the derivative becomes a squared minus x squared in the square root. And of course x has got to be between -a and a, so that then when you divide it by that dilation, you got between -1 and 1. And then finally the tan. Then our derivative is not a, we've not got the a yet, it's 1 over 1 plus x squared. And this time there's no restriction on x, x can be any real number. All right, And of course then if we stick our dilation in there, x on A, then the derivative, what ends up happening is you have an A on the top and A squared plus x squared. Of course, x can still be any real number. Alright, so they're the patterns. They're on your formula sheet. So you don't have to remember them. You just have to be able to recognise when they turn up in sums and then use them. Alright, 3 examples. And I'll rub this off. Yep. So first of all, I feel in the whole scheme of things straightforward. Example. So differentiate the following with respect to x, I should say. Alright. Part A. So if I've just got y equals sine minus 1, x on 3. Then, using the pattern, got to recognise that A is the number down there. So A is 3. So then when we're using the pattern for the derivative, pattern is 1 over the square root of A squared minus x squared, which in this case is 1 over the square root of 3 squared minus x squared, which of course is 1 over the square root of 9 minus x squared. And we do have a restriction, because what's underneath the square root has to be a positive number. So our restriction is that x has got to be between -3 and 3. Because if it's equal to 3, well, we get 0 with the square root of 0, which is 0, so it's 1 over 0, which is undefined. So while we can do the square root part, if it's equal to -3, we can't do the 1 over part. Alright, so that's why these numbers at the end here are not included. Alright, next one. Okay, so for this one, y equals cos minus 1 of 4x. Alright, now with the pattern, it was the pattern that's on the formula sheet, it's like x over a. And here we've got a 4 in front. So if we think what we're looking at, I'm just going to look at this bit here, do it in a different number. So this in here, this 4x, we need to want to write it in the form of say x over a. If I flip then times both sides by x. You find that a is a quarter. Yes? No?
Yep.
Maybe? So now that we know that a is a quarter, we can now use the pattern. So dy dx, because it's -1 over the square root of a squared minus x squared. So that's -1 over the square root of quarter squared minus x squared. Now with this here, we can fiddle around with this, which I will do because later on. So I've got 1/16 there. Yep. Correct. Now, if I, under this square root sign, go a common denominator of 1/16, it would be 1 minus how many lots of x squared? 16, did I hear you say? Well done. All right. Then, got that. Flip it, what a great idea. Alright, so yes, so now we can flip that and 1 times 4 over
Isn't it -1?
which then gives us -4 over the square root of 1 minus 16x squared. If we fiddle around. Okay, so the reason I do that, this is a bit neater maybe, but also later on when we get to the, going the other way, anti-differentiation and integration, we need to kind of start recognising that something like this we might be able to rearrange it or play around with it some way or other to get it looking like something like this so that we can then go the opposite direction. All right. Okay, so that's one option of doing that. There's also another way of doing it where you can use the chain rule, but if you really want to know what that is, I'll show you. But here is an example of something where we do need to use the chain rule. So last example for today. Alright, so all those patterns just had x or 4x or x over 3 or whatever. They didn't have another function in there. But now we've got another function in here that we're doing sine minus 1 of this other function. So now we need to use the chain rule because of that. So let u equal this stuff that's inside, so x squared minus 1. So then that means that y will be the sine minus 1 of u. Now, if we differentiate u with respect to x, what do we get? And if we differentiate y with respect to u, we get, the pattern is 1 over the square root of 1 minus x squared, but instead of x we've got u, so it's u squared. So far, so good. So now we're going to use the chain rule to put that together. So dy dx is what we're after, and that's dy du times du dx. Okay, and dy du was 1 on this stuff, square root of 1 minus u squared. Du dx is 2x. And I need to put my u back in here, don't I? Now the u is squared, but the u, of course, is x squared minus 1. So I've got x squared minus 1 in there, times 2x. All right. What can we do here? Any ideas? Expand, yep, so 1 minus, so when I expand that I will get x to the 4 minus 2 lots of x squared plus 1. Then 2x on top, on the bottom I've got 1 minus x to the 4 plus 2x squared minus 1. And the ones cancel out. What else have I got in there now? Let's go 2x minus squared minus x to the 4. What have I got there? A starts with C, second word F, common factor, of course we have, of x, no, not 2x, x squared, yep. So we've got a common factor of x squared, so that equals 2x over the square root of x squared times 2 minus x squared, I would believe. All right, 2x over, split that up, square root of x squared, and the square root of 2 minus x squared. Now, what's going to happen here when I square root x squared? What do I get? I'll get x, but do I need any more than that? Do I need plus and minus? Alright, so normally I would need plus and minus. Alright. So I've got the plus and minus there. Now what happens? Those x's cancel. So I've got plus and minus 2 over square root of 2 minus x squared. Now, this comes to the tricky part. The tricky part is the plus and minus in relation to all the x and that. Where does that, excuse me, where does that all apply? Anyone? Anything? No? Nothing? All happy with all of that? No? Yes? Maybe? Right. What it relates to is what we started with. So what we started with was that y was equal to sine minus 1 of x squared minus 1. So now what we've got to do is we've got to relate back to what this x squared minus 1 could possibly be. Alright, and sine, what's the biggest value of sine? And the smallest? -1. So this x squared minus 1 bit has to be between -1 and 1. Yes? So add 1 both sides, to everything. So 0 is less than x squared, or less than or equals, I should say, is less than or equal to 2. So then when we square root, we've got x between 0 and well, yes? That doesn't make sense though, does it? But what that's suggesting is that we've got two options. We've got between minus root 2 and 0, and then we've got 0 to root 2. Now, when we're talking about this plus and minus here, the plus version is going to correspond to one of those, and the minus version corresponds to the other one. All right. Now these are negative x's. So the negative x's will correspond to the negative answer, and these positive x's to the positive answer. All right. Because our answer in the end here has got to relate back to what we started with. So final answer is this. So dy dx was equal to -2 over square root of 2 minus x squared, or negative root 2 less than or equal to x less than 0. Actually, it's not equals. Is that the restriction on our x's all through that is just the, because we can't have over 0, can we? Right, so it's only less than, because we can't have over 0, it's undefined. Alright, so that's why we don't only have the less thans, not the equalses. Nearly forgot that. Alright, so between -2 and 0, it's that. And it's the negative version, but when it's between 0 and root 2, it's the positive version. All right. Anything you want to clarify there? Not that you can think of at the moment. All right. That's it then. Exercise 6C questions.